So
This is on Wednesday.
today we'll do this lab,
Boy.
and there's two parts to it. We'll talk about that. So then this is kind of the last of the kinetic stuff. And then we'll review on
Test on
Monday,
Tuesday?
and then the test over this stuff is going to be on Tuesday.
You
Okay?
should switch it.
No.
No, we're good.
Why do you want our test to be sooner?
Wednesday.
Oh.
No, shut up.
No.
Okay, never mind, I
No,
guess.
this is how it's going to be. That's it. Okay, so if you haven't handed in that assignment that was due yesterday, which a lot of you haven't,
Bless you.
I need that today. I'm growing weary of grading late work. Okay, so let's talk about what's going to happen with this lab. So you're going to take this cute little thing, it's called a cuvette, okay? And when you get this, you're going to see two sides to it. There's a side that has like ribs on it, and there's a side that is smooth, okay? So when you put it into the colorimeter, just pop this open, it comes open like this. Make sure that the smooth side is going to be in line with this light that's going to be shining through it. So you want the groove sides to be like on your right or left. You want the clear side to go like this. So when you put that in there and then you close it, so here's what's going to happen. The fundamentals of how this works is pretty simple. So here's this cuvette, okay? And you're going to have the groove sides over here. And then what it's going to do is it's going to shine a light through there. And what it's going to do is it's going to measure absorbance. It's going to measure how much of this light gets absorbed. So it's a crude analogy, but here's where chemistry meets biology. You're going to send a bunch of people across a forest opening. What it's going to measure is how many people get eaten by the bears. Okay? So that's basically what's going to happen. So if it's pure water, your absorbance is 0. That's like saying there's no bears. All of the people make it across. So the lower the value of the absorbance, that's reflective of more people going across. So the first thing that you're going to do is you're going to take this stock solution of 25 micromolar crystal violet, okay? Very distinctive color. So this has the capacity, because there's so much of those bears in the solution, it's going to absorb a lot of the people that are trying to make it across. So basically what this does is that it says, okay, we're going to send a certain amount of light through this cuvette. What it's going to do is it's going to measure how much of that light makes it to the other side. So if it's pure water, all of that will go across and your absorbance is going to be 0. So what you're going to do is you're going to start off with a cuvette full of this, okay? And you're going to measure that absorbance. So then what you're going to do over here on page 2, the first part of this lab that you have to do, is that you're going to prepare all these different solutions, A, B, C, D, and E. So the first thing that you want, you got to do the math, what the 12.5, 10, 7.5, 5, 2.5, what that is representing is the molarity of the solution at that point. So up here at the top, I tell you, assume that we're going to end up with 10 milliliters as the final volume in each case. So what you're going to do is you're going to use M1 V1 equals M2 V2. Okay, so you're always going to start, every time, you are going to start with 25 milliliters of the stocks, or the 25 micromolar. Okay? That's going to be your molarity initially. Your V1 is what you're not going to know. So what you're going to need to figure out is that, oh, I want my second molarity to be 12.5, and I want 10 milliliters total. Oh, okay. So I'm going to take 25 times 12.5 times 10. That gets me 125. I'm going to divide that over. So somebody take a 25 and divide that by 125. Otherwise known as? Yeah. So on this one, so what that's going to give you, okay, in this case, in this situation, if you think about this, you want 10 milliliters of a 12.5 molar solution. Okay? So if you solve this for V1, okay, so you want 25 and you want 12 and a half. So what you should see, hopefully, is that this V1 becomes 5 milliliters. So what you're going to need is 5 milliliters of the stock solution, okay? And then you're going to need 5 milliliters of water, okay? Because if you think about it, oh, I've got a stock solution that's 25. I take 5 of that, I double the volume by adding 5 milliliters of water. Hey, I end up with a concentration that's half of what it was. Now, this is the situation where you really need to measure this out precisely. Because if these concentrations aren't right, then what you're going to do for the rest of the lab is going to be a train wreck, okay? So you really need to get this mixed correctly. So then the next one, you need a 10 molar solution. So you're going to do the same thing. You got 25 times X is going to equal 10, which is what you want your molarity to be, and you want the final volume to be 10 milliliters. Oh, basically you're going to take 25 and divide that by 100, okay? And you're just going to keep going like this, okay? Which is oddly enough, actually you can take 100 and divide it by 24, and you're going to get 4 milliliters. So what that's going to tell you is that you're going to need 4 milliliters of your stock solution, 6 milliliters of water. And so what you should see on this trend is that because you want this stuff to be more and more and more dilute, you're going to need less and less and less of your stock solution and more water to make it more and more dilute. So here's what you're going to do. You're going to mix these up. Now, the first thing that you have to do is that you're going to take that stock solution of 25 milliliters, or 25 micromole, put it in a cuvette, put it in here, and when you get in the lab, these actually they work better if they warm up for a little bit. So when you get in there, first thing you do, grab a lab quest, get this plugged in. So what you should see is that when you put that cuvette full of the stock solution, you can change the wavelength of the light that's being emitted. You can change from 430 to 470 to 565 to 635. You should see a spike on your absorption. So one of these wavelengths should be much better absorbed than the other ones. Let me give you a hint. It should be the 565. Guys, these are notoriously sketchy, like in terms of being temperamental. So when you do this, and if you don't get a spike in your absorbance of 565, get a different one. And then let me know that, hey, this doesn't get that spike. Hopefully the ones that I've got out are the ones we tested last year, and they should be okay. So to change that, you've got these buttons down here. That's how you're going to change that wavelength. So remember, there's an inverse relationship between wavelength and frequency. So as the wavelength gets shorter and shorter and shorter, the frequency gets higher and higher and higher, and your energy gets higher and higher and higher. So basically what you're changing is the energy of those photons that are going through there. And you should see that you get a spike on one of those. So that's the first thing that you're going to do. Once you get that, eventually you're going to draw a graph where you're going to have concentration here and you're going to have absorbance here. Now, when you do this, especially what I found is that this is going to be very linear. If there's ever an outlier that doesn't really fit with the rest of the data, that's going to be that initial 25 micromole concentration. So what should happen, this concentration is going to go from 0 to 25. Your absorbance is going to go from 0 usually to about 1.2. Okay, 1.2 is usually like the high end on these scales. So obviously as your concentration gets bigger, okay, so let's think this through. As you have more and more of a concentrated solution, what's going to happen to the number of people that get eaten by the bears?
More people are going to get eaten.
Yeah, so what's this graph going to look like?
gonna be like a normal linear function with the
Yeah,
power.
hopefully, it should produce a linear function like this. Yes, you're gonna have to draw a line of best fit, okay? You're gonna have to draw a line of best fit. If you get one point, which notoriously might be this first one, that's way off that line, that's an outlier, don't worry about it, okay? Don't worry about it. But this notoriously produces a pretty linear graph. So you're gonna have to find the slope of this line. So what you've got is and this is laid out in the lab. What you're gonna use is Beer's law. And no, this has nothing to do with beer, okay? Don't, look, we studied Beer's law, that's cool. No, it's nothing to do with it.
Have you seen? Never mind. Actually, there's a documentary called "Beer Saved the World," and they drink beer, and that's what saved them on the Mayflower.
Okay. Have not seen that, but okay.
Okay.
Yeah, fun fact.
Okay, fun fact. Okay,
It's really fun.
so let's talk about this equation. So these first two numbers, don't worry about them, okay? Literally, do not worry about them. Just realize that they're numbers. So your A is technically, this is a technical thing, and I'll show you why you really don't need these numbers. This is known as your absorptivity constant, okay? And that changes based upon the solution, okay? So like crystal violet's going to have a particular one. Iodine would have a different one. If it's blue, it would have a different one, okay? It's just a number. Do not worry about it. Just realize that it's a number, okay? It's a number. B is what's known as the path length. So the path length is, in this case, when you look at a cuvette, what happened to my cuvette? Oh, here. So when you look at that cuvette, the cuvette is the length that the light travels through. You don't need that number, but realize it's just a number. So here's the importance of this, is that these two numbers here are not going to change within this lab. We're not going to change the type of substance. We're not going to change the path length of the cuvette. This is going to be a number. Don't care what it is. It's a number. Okay, it's just a number. So what we're going to do is we're going to take advantage of this is the fact, this is what Evan said. We're going to take advantage of the fact that this is going to be a linear function, y equals mx plus b. B is going to be your y-intercept. Y-intercept is going to be 0, because if you have no concentration, you have no bears. All of the people make it across, none of the people get absorbed. So this graph is going to start at 0, 0. So basically, yes,
So we're making our line of best fit, we should make sure that 0, 0 is a point?
yes. Make sure that 0, 0 is one of your points. So I would start at 0 and kind of pivot it at 0, 0, okay? So, because this is a linear function, this C is going to be your concentration. That's what's going to go on that x-axis. Oh, that's going to be 0, 12 and a half, 25, whatever that is. Okay, so that's going to be the concentration in your molarity. Y is going to be your absorption. That's what this machine is going to read. Okay, so your A is going to go off that. This is going to be your concentration. So what's going to happen when you find the slope of this line, basically what you're finding is that AB value, because that's going to be the slope of that line, because you have y equals mx. So m is going to be those values of A and B. They're constants though. I don't know what they are, don't care what they are. All I'm going to worry about finding is the slope. So that's the first thing that you have to do, and you have to get that done meticulously. Okay, because if this slope is wrong and not precise, the rest of the lab is going to be a train wreck. Okay, that's the first thing you need to get done. Get those, boom, line drawing. There you go. Now, the next thing you're going to do is that you're going to deal with this reaction. Oh, come on. Really? Oh, at times I hate technology. There we go. I just didn't tap the electrons down to the bottom of the pin. Okay, so, all right, so this reaction, what's going to happen, you can take CV plus hydroxides, and that's going to produce CvOH. Now, here's the cool thing about this reaction. Number one, it's a very slow little reaction, okay? It isn't like you take, hydrochloric acid and sodium hydroxide, boom, those react immediately, they neutralize this. So this reaction is handy because it takes a while, okay? It's a very slow reaction, okay? It's like watching, grass grow. It takes a while, all right? It isn't like we dump these together, boom, reaction's done, okay? It's cool, it takes a while. So this is color. This has a color purple. That's how we can measure that absorption. And then this is clear, okay? So what we're going to do is we're going to mix together a solution of Cv plus and sodium hydroxide. And we're mixing them together. Now, here's what's going to happen. As soon as that gets mixed together, okay, and over here on page 4, on line 8, you're going to mix 10 milliliters of your stock solution, okay? I say again, 10 milliliters of your stock solution with 10 milliliters of a 0.02 molar solution of sodium hydroxide. So, you're going to have them ready, okay? Boom, boom, mix them. As soon as they get mixed together, you're going to take some of that and you're going to put that into a cuvette. Now, this is why you need that second paper that I gave you today. What you're going to do is you're going to keep track of concentration or absorption as a function of time. So you're going to mix it together, boom, slam it in the cuvette, boom, slam it in the colorimeter. So at time 0, you're going to have a certain value of absorption, okay? Boom. Maybe it's 0.84. I don't know what it is. I'm just making up a number, okay? So here's the cool thing about what you're going to be able to do. Now you're going to work backwards. If you know the absorption is 0.84, then basically what you're going to do is you're going to go back to this linear function and you're going to go, oh, now I know my absorption, you know what your slope is, then you're going to solve for the concentration because that's what you're ultimately after. So by an indirect measurement of absorption, we could find the concentration. So basically what you're going to do is you're going to take that value of that absorption, divide it by the slope of the line, and then you're going to find your corresponding value of the concentration. Okay? So knowing absorption, take absorption, divide it by the slope, boom, there's your x value. It's just a linear function, that's all it is. So now, every 30 seconds, you're going to record your absorption. So if you look at this reaction, over a period of time, what's going to happen to the concentration of my Cv plus ions?
Goes down.
It's going to go down because it's reacting with the hydroxide, right? It's reacting with the hydroxide. So as the concentration of my Cv plus ions goes down, what's going to happen to the concentration?
Go down.
It's going to go down, so what's going to happen to my absorption?
Go down.
Right? Because there's going to be a direct relationship. So your highest absorption should be at the beginning, because that's when you have the most bears out in the forest absorbing the people. So as time goes by, you have fewer and fewer bears in the middle, more and more and more the people go across, fewer people are being absorbed by the bears. Okay? Makes sense. So you're going to do this for a period of time. Then that's going to be your first big step. Get your data. Okay? Then you can find your concentrations. Now, this is where we're going to determine if it's first order or second order. So then, knowing the concentrations, then you're going to take the natural log of those concentrations, you're going to take the inverses of those concentrations, and then you're going to draw a graph, and you're going to say, hey, which one is the most linear? Okay? So, you're going to end up with a total of 3 graphs. The first one is going to be the absorption and concentration one. Okay? That's going to be the first graph. You need the slope of that line. I would recommend that you make life simple for me. I'd circle the points on the graph, label those so that I know which points you're using to find the slope of the line. If it happens to be a data set, great. If it isn't, hey, you got to pick points that are on the line. That's the whole point of a best fit line. Then your second and third graphs are going to be time, and then you're going to have the natural log versus time graph, and then you're going to have the inverse of the concentration versus time. And again, if you want to put those all on one graph where you have time here, and you have natural log here, and you have the inverse here, and you put them both on the same graph, cool, okay? If that flips you out and you just want to draw them as separate graphs, that's cool too, okay? It's whatever works best for you. Okay, all right, so go in, let's get started. We'll see. The first thing you need to do, though, is plug in these colorimeters and get them warmed up.